We love strings, but the efforts involved in finding efficient solutions to these common problems that come up everywhere makes us doubt. The one-step solution being the suffix automaton, which manages all of this in linear space and linear time. But what really is an automaton? An automaton is nothing but a hypothetical machine that responds to input events and changes its states. For instance, this one here that validates whether a sequence has an even number of nodes, which is not the case for this. A deterministic finite automata is a five-tuple, where Q is the finite set of states, sigma the alphabet, delta the transition function, Q naught the initial state, and F the final accepting states. Now, an automaton's components can be represented by a graph like this, where Q2 denotes the final state, transition delta the arrow, alphabet the label, and initial state Q naught. Now, suffix automaton is the minimal such DFA that accepts all substring from input string. A suffix automaton can be understood as a directed acyclic graph, with nodes as states and edges as transitions. One state T naught, the initial state, is the source of the graph, from which all nodes are reachable. Each transition is labeled with a character. All transitions originating from a node must have different labels of these characters. This node, for instance, can't exist because we can't have two keys. A state is called terminal if from T naught every path along transitions to it spells a suffix of string S. All suffixes can be spelled by traversing all paths to the terminal states. For instance, for ABA, paths A, BA, and ABA are the suffixes that can exist and are traversed through the terminal states. And also for ABA, as B is not a suffix, the gray node is not terminal and hence intermediate, as there is a path to it from T naught only containing B. Now, similarly, let's consider string ABB. To figure out if the given structure is a valid SAM or not, let's consider the path from T naught to every node and figure out which nodes are terminal and which are intermediate. The right clean node has a path ABB, which is the string itself, and hence the suffix is valid. So it's a terminal node, as this is the only path. For the gray node, let's first see the left green node. We have A as the path, and is not the suffix, so it's an intermediate node. For the gray node, we have the paths as AB and B. Now B is a suffix, but AB isn't. So if we consider the definition of terminal states, we had all the paths that can be there from T naught to that state should be a suffix. So this can't be considered as a terminal state and also can't be considered as an intermediate state. There is a dilemma here. This undecisiveness can't exist, and hence there is a contradiction, making this structure invalid. Actually, the valid structure for ABB is something like this. You can validate it yourself. Now, before moving further, discuss some important notions that will be helpful in the future. One is end pause and one is suffix links. So, end pause is nothing but the set of end positions of a substring of S. That is, if you have a non-empty substring T of S, the end pause of T is the set of all positions in S where the occurrences of T end. So, let's try to play with it a little. Let S be all substrings of S with let S be all non-empty substrings of S. Now we define a relation R on S such that T1 and T2 belongs to R only if and only if n pos of T1 is equal to n pos of T2. Now we can prove that R is an equivalence relation because if T1 equals T2 then it's reflexive, and because of the equality it's both symmetric and transitive. So this shows that we can divide all the non-empty substrings of S, the set of all that, into distinct equivalence classes where each of them have their own interval, their disjoint. So this is an important lemma that we'll use later. Also, a key observation is that in the DFA, all the n-pos equivalent substrings correspond to the same state. That is, each state actually symbolizes the class, equivalence class based on the npos set relation. So, for instance, you can see for the string s equals ABA, if we list out all the npos of the substrings possible, you can group them in each state. You can group them together, and in each state, you can see that the npos values of the paths from T naught to that state are the same. Now, there is a convention that for the initial state T naught, we consider all possible indexes of the string as well as the state minus one. We'll see later how is it useful. Um, this is also a very nice. Okay, so now let's discuss three lemmas which will be useful later as well. Now, if suppose we have two non-empty substrings u and w, with u being less than w, then this lemma says that they are n-pos if they are n-pos equivalent if and only if a string u occurs in S only in the form of suffix of w. Now, the proof of this is obvious. If the string u occurs as the suffix of w and only as the suffix of w, then both have the same end positions and hence the same n-pos value. Similarly, we can prove the vice versa. Similarly, we have a lemma 2 that states that for non-empty substrings u and w, either their sets don't intersect at all, or the npos of w is a subset of npos of u if w has more length than u. Now, it depends on if u is a suffix of w or not. How does it happen? Suppose u and w have the npos of u and w have a common element, then you know that uh, both of them, there is at least one position in which both of them end. So this means that u is a suffix of w because the length of u is less than w. And if u is a suffix of w, then every occurrence of w, for every occurrence of w, we will have an occurrence of u. So npos of w will be a subset of npos of u. Otherwise, obviously, there will be 5. So this is a cute little lemma which we can use later. Now comes the third lemma that if you have an npos equivalence class and we list all the substrings in that class, then all of them will be the suffix of the longest one, and there will be a shortest string till the length of the shortest string. So basically, if suppose the length of the shortest string is x and that of the longest string is y in the same npos sequence class, then the whole interval from x to y is covered by the substrings in linear increments of 1. For instance, if we have abcbc, let's consider this string and consider BCB as its substring. The npos of BCB is 3, npos of CB is 3, and npos of B is 1, comma 3, which is different from both of them. Hence, CB and BCB are part of the same equivalence class. And CB is a suffix of BCB. CB has the minimum length 2 and BCB has the maximum length 3. And although this example is a little trivial, but all possible lengths in 2, 3 are covered by the substrings. Now, what's the proof of this? Obviously, let's try to denote u as the shortest suffix of w in the same class, where w is the longest substring of that class, and say that we have so say k as the suffix of w, which is there in the class and has more length than u. Then, because u is the suffix of k, whenever u exists from the lemma, whenever u occurs, k will also occur, and hence k will be a subset of u. But at the same time, because u and w have the same npos set, and w is again k is the suffix of w, so w npos set will be a suffix of will be a subset of that of k. I can prove that the subset of k, the npos set of k will be equal to that of u and w, and hence k will be in the same class. A few simple definitions that might be useful later. For any state v, hence for the same equivalence class, we can define longest v as the string with longest length, which is w in this case, and len v as the length of longest w, string w. So um, whenever we will be discussing about a finite automaton structure, we will be denoting that state by the string of the longest length in it. Similarly, shortest v is u here in this case, and min len v is the length of u. So maybe we'll use these two functions later. So here we are with suffix links, yet another important concept. Now, consider state v with the longest of v being w and the shortest of v being u. Now, if the length of u is greater than 1, this means that w has suffixes which have lesser length than the shortest suffix in the same equivalence class as w. This means those suffixes will occur more than when w occurs, and hence will be in different equivalence class. So suffix link actually captures this very well by the definition and says that the state that corresponds to the largest suffix of w that is in a different equivalence class than it corresponds to the suffix link of v, where w is the longest v, right? So from this, you can directly say that the longest such suffix that is not in the class which you're saying can easily be extracted from the definition of u. U minus 1 character is in different class, and hence length of link of v is just nothing but the length of u minus 1, or million v minus 1. Now let's consider some lemmas that may actually be foundational in designing the algorithm. First, suffix trees form a tree with root T naught, or lemma 4. Now, how do we say that something forms a tree? We have a certain constraint between parents and children, and if we can somehow manage to go to the root by paths, and every path leads to the root, we can say that we have a tree. So suffixes have a very nice property that the length of the strings continuously decreases and always decreases. So eventually you will always lead yourself to the root naught, which is the parent of every such particular state, and hence suffix links form tree. Another lemma of following this is the foundation, or is the connecting link between endpause and suffix links. So this summarizes our whole discussion very well, that if we construct a tree using the set endpause, say by the rule by setting that the parent node contains a set of all children as subsets, then the structure will coincide with the tree of suffix links. Let's just take a look at an example to have a better clarity. So for the string ABB, if you list out all end pauses and try to make a tree such that T naught has the universal kind of end pause for the string, and if you try to list out all of them, then you see that the states that are formed have the longest strings in them following a trend of suffix links. Now B is a suffix link to AB because B occurs more than AB and is a suffix of AB, and similarly with ABB. And T naught obviously can be considered as a universal suffix of every particular substring of S which is non-empty. So this is also a suffix link. A quick proof for this small lemma can be that that you can form a tree using endpause by this way, because um, the parent node, if is a suffix of the child node, then parent node obviously contains the sets of a child node as subsets in its endpause. So the endpause of parent is a superset of endpause of children. And for suffix links as well, as you were creating suffix links from suffixes itself of states which had um, difference in them only because the occurrence of suffix was different, and you had the immediate most equivalence class in which you had the longest string behaving as such. In um, suffix links, you can directly relate suffix links to the fact that you have endpause of parent as the superset of endpause of children. So this might be a clearer interpretation of what it is really. So we are closer to getting to know how exactly is this non-intuitive structure correct, suffix automaton. Now for your reference, you can just pause for a moment and try to digest. This is yet another diagram in which I try to merge the suffix automaton along with the suffix links to form a sort of web of substrings of ABCBC. Now finally, Let's discuss the awaited algorithm of constructing SAM by scratch. Now, this is an online algorithm where we add each character to the string and append SAM accordingly. So, as we promised that this algorithm takes linear space, we store the minimum number of variables, len, link, and the list of transitions from every node that we can store in form of a map. So, first, we try to initialize our system. Initially, there will be a initial state t naught with length 0 and length -1, which is for our convention. So let the current string be s and we add the character c to it and see how the suffix automaton changes. So now let last be the final accepting node of the final state machine for string s. Now I create a new state curve because a new class will be created as you add a character. Now for this curve, we know that the length of this node must be one more than the length of the last node because of the addition of the character. But we don't know right now. We don't know about the link um, for this. So we'll try to derive it from the third step. Now to link it with the tree, we start at the last, right? And while there isn't a transition through C, we'll add a transition to state curl using C, right? From the node that we were before. And then follow the suffix link up till we get -1. This way, we append C to each suffix of S and hence create a terminal line of chain to the node, to the final node curve. Okay, so if finally we arrive at -1, this means C is a new character for the string and hence we add the link of curve to be 0 because then it will directly be linked to T naught, as you can see here. Now, but suppose that this node is P for some P in the tree where P has a transition C to stay, say, a node Q. Let's analyze the situation of what exactly it means and how can we relate curves link through P. Now P is generated by going up the suffix link tree from last. This means that P is the longest string in P is a suffix of S. Let the longest string of P be X. Now, as there is a transition through C, X plus C is a suffix of Q, hence a substring of S. And as P is the state at least height in the suffix link tree, X plus C is the longest such suffix of longest in curve, that is the longest string in curve, because x is a suffix of s and hence x plus c is a suffix of s plus c. So x plus c is the longest suffix of the longest string in curve that is not present in curve. So the state containing x plus c must, the state containing x plus c as the longest substring must be the suffix link or the new node curve. Now, hence we have two cases. It may be possible that this state is Q itself, or it may also be possible that there is no such state present in the suffix attribute. So hence, let's first discuss a simple case where Q is itself the state that contains x plus c. That is, if say x is the longest string in P, then len P plus 1 is the longest string in Q, which is x plus c. So in that case, as we discussed before, we know that the suffix link of cur is Q. Then we leave it there and our situation is sorted. For instance, let's take an example of ABA. As you can see in this automated, that as you add ABA to AB, which was last, AB had a suffix link to T naught. But because you added ABA to AB through the transition A, using the third step of the algorithm, we tried to go up the suffix tree of AB and see that T naught is the first node where transition A is used because you can't add a transition of A from T naught to the current node. Hence, P is T naught and Q is AB significantly. Sorry, Q is the node containing A. Now, because we know that the node containing A is having len 1 and T naught has len 0. So this means that this is the case of len Q being the link of the current node, and hence we just add a suffix link from ABA to A. So this clears the first case. Now let's discuss about the second case. The second case arises when there is a non-continuous relationship between Q and P in terms of suffix links and transitions. So what do we do now? Because we know that there is no node of length 1 plus length P, we have to create a clone of Q. And why do we have to create a clone of Q? Because Q is the closest node to this hypothetical node that can qualify all the properties, just except the length. So we split Q and we clone it such that only the length differs while the transitions and the links are the same. Let's name this um, node as clone, and we define the length clone as length p plus 1. So this is definitely the suffix link target for our string curve, for our state curve. So hence, link curve is clone and link q is also clone because q has a suffix as x plus c, but while x plus c is the longest string in clone, the end cause of q must be a subset of end cause of clone, as clone's longest string is suffix of q. Now let's take an example of s equals ABB. Now as we add ABB, or the last character B, to S, where AB was the last node, we see that as AB had T naught as its suffix link, and T naught have already transitioned through B, we must have a problem of having found state P in the suffix tree, in the suffix automaton. Now, here, because len of q as AB is q now, so len as len q is 2 while len p is 0, we no longer have len q equals len p plus 1 and hence have to make the clone. So we try to design a clone of the state q and which has len 1 but the same link as of q to p, which is t naught. So there must be a transition from t naught to clone to b for making that happen. And the transitions from Q to the other nodes must also be preserved. So this clone has a transition to ABB by B. Now here is a good catch. Once we have done this, we know that now, so by this, and also we know that Q's suffix link is clone and ABB suffix link is also clone. So we have updated both of these relations together. Now, one thing is beautiful here to understand that Q, we are not done yet because the express C string will get repeated if we do this because there is an existing transition from P to Q or any suffix link of Q which may not have been P, which has the transition C. So to eliminate all that possibilities, as clone is the suffix link of Q, I don't want them to generate x plus c inside Q so that we have 2 times x plus c in our automaton as each substring only occurs once. So we walk along P's suffix link and while there are transitions through C to state Q, we redirect all of those to clone. As you can see from the diagram, we try to redirect this transition to that. And that actually symbolizes the same structure which we looked a while ago when we were trying to validate suffix automatons. And last but not the least, as we have proved, we have tried to identify all the nooks. We update last to curve. So this completes the algorithm. Just you have to keep on adding C and repeat these steps over and over again until your string S finishes. Hope you enjoyed this journey with me. Thank you.